Okay, once we have got all these results, next step we go for solving the Kepler's problem. So these are some of the mathematics you will require while solving few problems, and therefore I have included here x by a equal to cos hyperbolic a in the general case, and y by b equal to sin hyperbolic. This is the expression we have taken. So sin hyperbolic f is equal to y by b, and this y will nothing but sin theta divided by b, because this is your r and this is the angle theta, so this y becomes r sin theta. And r equal to L by 1 plus e cos theta, a times e square minus 1 if we write in a positive mode. A cancels out and we get a square plus a square minus 1. So a square minus 1 under root sin theta divided by 1 plus e cos. And this is your sin hyperbolic. Now we need to find out f. So in the Kepler's equation, sin hyperbolic f appears. So this is the part there, and then also we can look into the cos hyperbolic f function, which is 1 plus sin hyperbolic square f. Plus m square cos square theta plus m square 3 times cos theta plus m square minus 1 m square theta. And plus cos theta, which is cos theta plus cos theta divided by theta. These two can be combined together to yield 1 e square. So this is 1 plus e square plus 3 cos theta minus sin square theta. And 1 minus sin square theta is nothing but cos square theta. So this is of the formula, and then divided by 1 plus e cos theta whole square. And this is 3 plus cos theta whole square divided by 3 plus e cos theta whole square. Cos hyperbolic f. All these information are required for solving problems in this domain. Now finally we find out h. on the previous page. This can also be written this way. Now also we have f equal to sine hyperbolic z equal to ln z plus z square plus 1 under. So what we have done that we write this quantity as z. This is equal to write z. So this is sine hyperbolic inverse z. And then you can see from this place that during the previous discussion we have obtained the two expressions. You can go back and look into this. F equal to ln x plus x square minus 1 under it. This is the expression we have derived as the shaded area in terms of shaded area or angle whatever. So here this z, once we have written this quantity as f equal to sine hyperbolic inverse z, the sine hyperbolic f equal to z. So already all the expressions we have worked out, and only using those equations. Earlier we have looked into this expression we have got sine hyperbolic f equal to y equal to x square minus 1 under it. So this can be written as sine hyperbolic inverse y, and then this can be proved that this quantity is y square plus 1 under it. So do this as an exercise. So with this information, so work out this. This is whatever we have done for the cos hyperbolic along the same line. This can be proved, where y is related to y equal to x square minus 1 under it. So
Sir,
here, yes,
sir, that is y square plus 1 or y square minus 1?
which one? Y square plus 1, not minus 1.
Okay, sir.
This is plus 1. Okay, so cos hyperbolic f, we wrote the expression for cos hyperbolic f equal to e plus cos theta divided by 1 plus 2 cos theta, and sin hyperbolic f equal to e square minus 1 under root sin theta by 1 plus 2 cos theta. These are the two expressions we are using. So finally, what I told you that put this in the proper format. This is ln z plus z square minus plus 1 under root. Okay. So this we need to work out as an exercise. So we look at this quantity z plus z square. Instead of writing x, I am using the z symbol here. Z plus z square plus 1. How much this quantity is? So z is here. Of course, we can write in terms of the z equal to sine hyperbolic f. So this quantity sine hyperbolic f, just now we have derived, this is d square minus 1 under root sine theta divided by 1 plus e cos theta.
Sir,
Ah,
sir,
oh, I am
it's
writing on the
overlapping.
same page. Okay. So what we are interested in finding this quantity z square plus 1 under root. And z, as per the earlier derivation, we have equal to sine hyperbolic f. And sine hyperbolic f we know, so this will be 1 plus sine hyperbolic f under root. So sine hyperbolic f plus 1 plus sine hyperbolic f under root. And sine hyperbolic f is e square minus 1 under root and sine theta divided by 1 plus e cos theta and plus 1 plus minus 1 minus square theta divided by 1 plus e cos theta whole square under root. So this quantity already we have expanded and worked out. This is nothing but e cos theta divided by 1 plus e cos theta. And the last page we did it. And this is e square minus 1 and theta by 1 plus e cos theta. And therefore, f equal to ln z plus z square plus 1 under root. This quantity gets to ln z square minus 1 under root and theta divided by 1 plus e cos theta. It's a common in the denominator, so we can write it this way, e plus cos theta. Now if we use the identity sin theta equal to 2 times theta by 2 plus 1 plus minus cos theta by 2 and cos theta equal to 1 minus if this identity is used, then this can be reduced to the format f equal to ln e plus 1 under root plus 2 minus 1 under root and theta by 2 So we have all the related information available to us. So if we put it in the Kepler's equation, m equal to e sine hyperbolic if we write it in the Kepler equation, m equal to e sine hyperbolic minus sine hyperbolic f minus f. This was our Kepler's equation. So this becomes E times E square minus 1 under root sin theta and divided by 1 plus E cos theta, and minus shift is nothing but your ln. So this is the Kepler equation in terms of the hyperbolic anomaly, while this is in terms of the true anomaly. So if it is given that you have time t1 and t2, or right from the beginning, from the perigee, you want to measure what will be the position of the satellite at time t in the hyperbolic orbit. So what we need to do, find out n. This is equal to n times t minus tau. N is available to us if the semi-major axis is available. Time is given to you. Tau is the time of perigee phases, which may be set to 0 if nothing is given. Okay, so m will be available from this place. Then solve this expression. This expression can be solved iteratively. So either you can solve this or either you can solve this. So once you solve this, so directly from here the theta will be available. So what we are doing, that we are solving for m, and then we can solve for f, and then can solve for theta, or directly using this expression we can solve for theta. So if theta is known, and then r will be known to you, r equal to L by 1 plus v cos theta. So r is known, r and theta both are known. Other parameters of the orbit, they will remain constant, and therefore the future position of the satellite can be worked out. So if the satellite is, the orbit is not getting perturbed, so these are the only two parameters that you require to work out the whole Rn. Yeah, of course, E is known to you, and therefore L is known here, E is known here, so everything is known. So the future R and future theta value, once it's known, so the x, y, z coordinates, they can be computed on. So you need to do some exercise yourself, and moreover, you should also remember that whatever we have worked out earlier, this result is important. So this is just like playing with mathematics. As much as you work it out, the things will be always true.
Sir, sir, that should be tan hyperbolic e by 2 or just tan e by 2?
Tan hyperbolic equation.
Okay, sir.
This is because here in this case we are discussing about the hyperbolic function. This is not just that we have done earlier. If in the elliptical case we have, while we have done, so there it appeared as okay, this place. This is tan hyperbolic E by 2. Here also tan hyperbolic E by 2. This we are discussing in the case of the hyperbolic
Yes, sir. Yes, sir.
orbit, and therefore this is applicable here. Yeah, I have done all these mathematics, but I don't know if doing that much of mathematics is being used here. So everything is derived. A few other things you can do it yourself. Now the last part remaining is proving the R equation. The R expression we have used, and I told that we take it for granted. So I will just work out that part. So we have R equal to L by 1 plus E cos theta. You can put it like this, and then 1 plus E cos theta is, now cos theta expression it can be written as E minus cos hyperbolic F and cos hyperbolic F minus 1. And then in the numerator, E plus hyperbolic F minus 1. Okay, here in this case, what we have done that, okay, let me write it this, and thereafter we will do the other things. This part it cancels out, and then we are left with E cos hyperbolic F minus 1. E cos hyperbolic. Here what I meant that I could have written here with a minus sign in this place, or say simply L equal to A times C square minus 1. Instead of writing this, so this would have cancelled out, and then minus sign would not have appeared. So in that case, the expression will appear as A times E cos hyperbolic F minus 1. So it depends the way we are writing. So here in this case, A is a positive quantity. Here in this case, A is a negative quantity. The other way of doing the same thing is R equal to A times E square minus 1, which is L, and then 1 plus E cos theta. So this is E cos theta 1 minus tan square theta by 2 tan square theta by 2. Tan theta by 2 already we have written. You can work out that tan theta by 2 in terms of tan hyperbolic function. So this is E times 1 minus e plus 1 divided by e minus 1. And how you will get this tan hyperbolic in terms of, already we have described this cos hyperbolic f, how it's related to, or sin hyperbolic f, how it's related to your cos theta function. Okay, on the previous page we have worked out. So there you can break it in terms of the tan hyperbolic f, this cos hyperbolic function. Okay. And similarly, on the right hand side where the cos theta is appearing, it can be broken in terms of tan theta by 2. And once you break it, so it will come here in this format where on the previous page we have written this result, this particular expression. This can be worked out. So you just use the cos hyperbolic function. It's a connection to the cos theta, and then that expression can be obtained. So from here, this can be simplified. And if you simplify it, so this will simply give you result. So the rest of the things are just mathematical manipulation, so you can check it yourself. E cos hyperbolic f minus 1. Here a is greater than 0. Whenever we write here equal to e minus cos hyperbolic f, so in that case a is less than 0. E is always greater than 0. E will never be less than 0. So using all this information, but this part it becomes complicated, as because there are number of mathematical expressions involved, and if we want to work it out, so it will take a lot of time. So let me bring some paper. I will take a break. Paper is over. Two classes of problems, they arise in the Kepler problems. Classes problem arise from Kepler's equation and to travel between 2 points. between 2 points. That means the theta 1 and theta 2 are given. So theta 1 and theta 2 is given. So from here we can get E1 and E2. Time to travel, remember. This is the time you have to find out. And from E1 and E2, delta M can be computed. And once delta M is known, so this delta T can be computed. So given theta 1 and theta 2, so what we are say the hyperbolic case, what we need to do, we have written the expression as m t minus tau equal to e sine hyperbolic f minus f. So first of all, we need to work out f1 and f2. So from here, this will be m1 t minus tau equal to e sine hyperbolic f1 minus f0. Similarly, we will have m2 t minus tau e sine hyperbolic f2 minus. So once f1 and f2 are known, so that means the right hand side is known. Let us say this we write as capital X and this we write as capital Y. So the right hand side is known. So from this place we have m1 t minus, so we write here t1 and this we write as t2, m1 and so how much time it is going to take? This is the question. So t2 equal to y divided by m2. Our if we take tau equal to 0. And similarly t1 equal to x divided by m1. So the question given was the theta is known to us, and then we have to find out time to travel between these 2 points. So from that theta, we are trying to find out the values of E. Here in this case, we should not write E, but rather the F, the hyperbolic anomaly. Once the F is known, so we will have, if directly these things are known to us. Once we subtract them, m2, this becomes m2 times t2 minus m1 times t1 equal to y minus x. And this becomes m times t2 minus t1 equal to y minus x. So this t2 minus t1 is available. M is same. In the same orbit you are looking for, so the mean angular rate is going to be the same. Unless you change the orbit, m will remain the same. So if the eccentricity of the orbit changes, and consequently the orbit description will change, and in that case only the m is going to get affected, otherwise it's not. So from this place directly this is available to you. So this way various problems can be connected, and also we are aware of m times t minus tau. This quantity is directly written as m, where n equal to mu by p2 under root t minus tau. So mean angular velocity, this is a constant. This is not going to change. So whatever way the problem appears, if you utilize all the information till now we have discussed, the problem can be solved. So the first problem is that the time to travel between 2 points on any type of orbit, be it the hyperbolic, it may be elliptical, it may be parabolic. For all of them, we have worked out the expression. In the case of parabolic, we have not done it in terms of the eccentric anomaly or the hyperbolic anomaly, but in terms of true anomaly. The second problem is the stated light. The location of the satellite in the orbit after a certain amount of time. And this is called the propagation problem. Or ephemeris propagation, many times we call it ephemeris propagation. The initial r theta is given, and after certain time you have to find out what will be the r0, theta 0, the velocity, etc., whatever is involved. So this problem too can be solved. Vital element technique. Where you have to only propagate the true anomaly. Propagation required. The other elements propagation not required. FG method. The F and G are functions. So given the initial velocity and position using the FG method, so this is only for the thrust free case. This is also thrust free case. Another one is called the universal variable method. This is used for the boundary cases where E may be equal to 0.999, something like this. So the difference between the parabola, hyperbola, and the ellipse, it becomes blurred. So this is for boundary cases. So for this case, you can look into the introduction to astrodynamics. Astrodynamics by David Valado. Or there is a book on mathematics for astrodynamics by Richard Bartin, or Bartin. There is mathematics for astrodynamics. It's a very good book. It's called the Bible of Astrodynamics. Many complicated mathematics during the last 500 years, 600 years developed, so everything is there related to astrodynamics. So in the case A, what are the steps involved? Convert RV.
Sir,
So we are going on the same page. We say convert RV to the orbital elements A, E, I, capital omega, small omega, and theta. So only this quantity is a function of time. Rest others are constant, so theta can be propagated. And then propagate theta. And this can be done using the numerical method or the method already we have discussed, using the eccentric anomaly or the hyperbolic anomaly. So whatever the time you are looking at that time observe the mean anomaly. And then reform position vector and velocity vector. So we will do some problems, so things will be obvious. Case B we will do here. So this is also applicable for no thrusting case. As soon as you thrust, then the things will change. Applicable to no thrusting case. And C we are not discussing here, so you refer to the book. So FG series method we are going to discuss in this. In this method, for the planar case, you can work it out. Initial position vector is given. Initial velocity vector is also given. Z0 dot 1 cat plus y0 dot. Now R cos V0, this can be written as, this is R, the generalized formula. Cos V0 expand it. So this part becomes 0 x0 times x times y0 dot, and this will be equal and C1 become minus, so this is y times x0 dot. Okay, see here what I have done the actually in the FG series method, instead of writing here x, we write here this as a function of f and g. And this part is okay, our description of the radius vector, and then we describe r as a function of f times r0 plus g times v0. Means they are the future radius vector will be function of the initial position vector and the initial velocity vector. Similarly, the velocity in the future will be function of f dot times r0 plus g times v0, g dot times v0. Why? So once we differentiate this quantity, r0 and v0, they are constant. They are not varying. They are initial position. So just we can write it here in this case. So this is your r and v.
Sir, and F and G we have to derive.
We have to work out from here. So this quantity, as we have worked out here, r times v0, so this can be expanded. So v0 is a constant given in the right in the beginning. So f times r0 plus g times v0 plus f times r. This is fine. So r equal to f times r0, b times v0, and plus v0 cross v0 equal to y0 dot minus y times x0. So this term cancels out, and we get here f times r0 v0 is equal to f times h equal to xy dot minus y times x dot 0. And here also we have to take into account the vector e1 cross h times y dot 0. So e2 is e3 cap, and similarly the minus 1 will come in. So this is e3 cap. So magnitude wise, this becomes fx equal to xy x times y0 dot minus y times x0 dot. So the function f can be written as x divided by xy dot minus y times. Or say we can write f equal to x times y0 dot minus y divided by x. What we have written on the same thing we have written. So f times h we have written here in this case. This we can reorganize and write here f equal to minus y times this implies f dot will be equal to f dot y0 dot minus y dot, because x0, y0 and h are constant. Along the same line, We can also work out the other term. So G times V0. R0 cancels out. So we are left with G times R0 plus V0 equal to G times H. And this can be expanded again. So R0 is R0 times C1 cap plus H0 times C1 cap, Y0 times C2 cap. H0 times Y minus Y0 times X. G equal to H0 Y minus Y0 X divided by and once we expand this part, so this will get reduced to G dot Fh minus H dot H. So that means H dot G dot S minus H dot G equal to B. So we have got expression for it. We have got expression for connecting F and G, and also this expression we have got here in this case. We got it also available. Rest other things can be worked out in terms of the X and Y. Aerodynamics, many times it happens to be pure mathematics. In some cases the physics is involved, but mostly it's mathematics. Sometimes the mathematics becomes very complicated. As we progress, we will see that it's getting a lot more complicated. We can use these expressions r equal to L by 1 plus E cos theta. If we expand it, it can be written in this form. Already we have done this part in the orbit determination problem, so I am not repeating it here. So this expression can be written as minus r sin theta times theta dot, sin theta times theta dot is equal to h by r square. R dot equal to mu times T sin theta divided by h times cos theta. H sin theta divided by r plus this can be simplified a little bit by multiplying the up and down by 12. It is gets reduced to h sine theta divided by r plus mu times L is h square. So this h square divided by h becomes h. L by r is nothing but 1 plus e cos theta. So this is minus 1 minus e cos theta and plus e cos theta. So this gets reduced to h dot equal to minus mu by minus h by L minus h by L and the distance of minus h by L sin theta. So if we multiply up and down by mu, so this can be reduced to so if we take time to compute this part, we can do whatever is possible and do next time. Similarly, y dot can be written as mu by h e plus cos theta. Along the same line, y equal to r sin theta, we have to differentiate and work out. So therefore, h dot 0 is equal to mu by h sin theta 0 and y0 dot equal to mu by h e plus cos theta. Now f equal to x times y dot 0 minus y times x dot 0 divided by h. So we need to insert all the quantities here. So x equal to r cos theta, we can put it outside. And y0 just now we have derived mu by h e plus cos theta 0 minus y equal to r sin theta and times minus mu by h and sin theta 0. And theta 0. Mu by h and theta 0. This will get reduced to mu by h, we can take it out common outside, so mu by h square, r can be taken out, cos theta times e plus cos theta 0 plus sin theta times sin theta 0 cos theta minus theta 0. Here r equal to h square divided by mu 1 plus e cos theta E cos theta equal to h square by mu r minus 1. Then we can work it out and write it this way. E cos theta we can replace here in this case. So that becomes mu r by h square and r can be written as L by 1 plus E cos theta h square divided by mu and 1 plus E or theta 0 times cos delta theta minus sin theta 0 times sin delta. So what is the thing that whatever the delta theta you are looking for in terms of the initial position and the final position, everything is known. So we can conclude it fast. So thus we have E cos theta 0 equal to h square by minus 1 sin theta 0 equal to h times r 0 dot by mu and substituting in the previous equation, substituting we get r equal to h square divided by mu and 1 by 1 plus e times cos theta 0. So cos theta 0 is our writing here in this case. So e cos theta 0 will take inside, so this we will eliminate. This becomes h square by mu r 0 minus 1 times cos delta theta minus e sin theta 0 h r 0 dot divided by mu and sin delta theta. The future position is known in terms of h, which is known right in the beginning. Mu is also known. All the quantities here, they happen to be known, and only thing delta theta after this angle, what will be the position, so we will be knowing that. So everything can be now included in these equations. We will have f equal to 1 minus mu by r h square times 1 minus cos delta theta until unless we do some certain problems on this, the whole process will not be very much clear how we are going to utilize this. Okay, so using the same process, this can be worked out. Okay, so next week we will take up some problems, but on Monday we will have Viva. And for everybody, because there are total 12 number of people, so maybe 5 minutes for each of them, and as it appears in the call list, we will be called that day, and then 5 minutes will start. And instead of providing 30 marks, I will split it into a multiple of Viva so that the things remain balanced. And one final exam will be there. Okay, so whatever we have discussed, the FG series method, it's just a description. Don't take it that I have explained you everything. Once we go through the problem, so all the things will be clear, how the things are taking place and why we have done this. But the rest of the things, whatever we have discussed, it's the FG series method. Here the tan hyperbolic one. These are all mathematics, and you need to be, for working out the problem, you will require a lot of mathematics from here and there. Only then the problems can be solved. So if you have any question, you can ask me. Forget about the FG series method, because time was short. I have just covered the description. Next time we are going to discuss all those issues. So if you have any other question, you can ask me. Okay, if nothing, then we just respond to your attendance. Shivam Meena.